Okay, so let's start the content of the course. The first thing that we want to talk to you about is dimensions. They're super powerful. Use them. The older I get, the more I rely on the dimensions of a problem to help me make sure that I don't make any mistakes in solving it. So to kind of hammer this home with you guys, we're going to do a quick problem where we look at what is the drag stress on two moving plates separated by a fluid, and we're going to try to find a model for this drag stress just using units. So the first thing we're going to do is we have a plate here moving with some velocity v, a stationary plate on the bottom. These plates are separated by a distance h, and the fluid has a density and a viscosity. So the first thing we're going to do is we're going to write down all of the parameters that matter for this problem, and it's the velocity of the plate, the density, the viscosity, the height between the two plates, and the shear stress, because that's what we're solving for, obviously. And these are two infinite plates, so the area of them is unimportant. And now if we write down the units that each of these things have, the units on velocity are a length per time. Units on density are a mass per length cubed. The units on viscosity are a mass per length time. The units on height are just length, that's easy. And the units on shear stress is a little bit harder. It's a force per length squared, right? That's probably what you remember, newtons per meter squared. But if we break that down, we can show that that's equal to a mass length per time squared, that's kilograms meter per second squared, over a length squared. Those two cancel out, and we find out that length canceled out, not the time. We found out that's equal to a mass per length time squared. So we know that tau has units of mass per length time, and we want to set that equal to some combination of our other parameters. Well, we know we have to get a mass in there because we have a mass per length time, and it has to be on top. So that means we could choose either density or viscosity. And well, we know that viscosity has to deal with resistance to flow, so we're going to assume it's viscosity right now. It's not cheating, really. And then we have to, if we write down the units for that above, we find out that's equal to mass per length time, which is mass per length time squared. So we need to still get another time in there. If we multiply by a velocity, that will get us a length per time. That gets us our time squared, which is great, but it cancels out these lengths, which is bad. And so what we need to do is divide by a length. And so we can do this. And it turns out this is actually the equation for the shear stress on this plate here or here. It's a symmetric problem, so either this plate or this plate will experience this shear stress, which is equal to the viscosity times the velocity divided by h. In fact, at every point for a Newtonian fluid, tau, the shear stress, is equal to, in the dimensions on this matter, and we'll talk about this a lot, this is x, this is y, is equal to mu du dy, where u is the x component of the velocity. Spelled that wrong. X component of the velocity. And so what this is this is the change in velocity in the y direction, change in the x velocity in the y direction. So if we had to guess what this velocity looked like between these two plates, we know it's 0 here at this base, and we know it's at a velocity v here at the top. And in between, there's no reason to think it doesn't vary linearly, right? So the slope, the change in x velocity as we move up, is the same throughout the fluid, which is why the shear stress is actually the same throughout the fluid. Okay, so this just some vocab here. This viscosity here is the dynamic viscosity. For a normal fluid, quote unquote, this is a constant. And we will talk about non-normal fluids here in a second. In another note, this term here is a strain rate. Okay? So a quick question about that. What are the units on strain? So strain, which if I remember right is usually given by like a gamma, is equal to a change in length over a length, which is equal to nothing. It's unitless, right? But if a strain rate, if we take this, it's going to be times 1 over the time, which gives us a 1 over time. So the units on a strain rate are actually 1 over time. So if we look at this, du dy, we have a we have meters per second divided by meters. The meters cancel out and we get a 1 over seconds, which gives us a strain rate. So that's just an important thing to remember. And the reason why we have to deal with strain rates is because of the definition of a fluid. So when you took solids, right, whenever a stress was applied to an object, that stress produced a deformation, a strain, right? And you could solve for that strain. What makes a fluid different from a solid is that a fluid deforms continuously under a stress. You'll hear people say that, a fluid fills the container that it's in, which is also just a way of saying that it deforms continually under stress, right? Because the stress might be pressure or stress due to gravity and unequal. Actually, it's usually just due to pressure because part of the fluid is being supported by an object and part's not, and gravity's acting on the whole thing, which is why it fills the container, right? But you're going to have gradients in your stress, which are going to cause a strain rate or shear in the fluid. Great. All right. So Newtonian fluids and non-Newtonian fluids. A Newtonian fluid, like we said, the shear stress is a constant. So if we were to plot tau versus du dh, which is our shear rate, if we double our shear rate, we double our stress. Where this is y, this is x, and mu is equal to y over x is equal to tau over du dh, right? This is our ratio. That's a Newtonian fluid. So water's a Newtonian fluid. Alcohols are Newtonian fluid. A lot of oils are Newtonian fluid, right? Non-Newtonian fluids behave differently. So there are 3 different kinds of non-Newtonian fluids. One is called a yield stress fluid. So a yield stress fluid, which we'll do in blue, requires a certain minimal stress on it before it will start to flow. So instead of flowing immediately, you have to push on it by some amount and then it will start flowing like a fluid. This is a yield stress fluid. Can we think of any kind of yield stress fluid? I'm going to let you guys pause the video, do some active learning. All right. So if you think about a bottle of something that you have to hit before it will flow out, like ketchup, that initial hit creates a sufficient shear stress in order to allow the ketchup to start flowing. Toothpaste is one. Oops. Toothpaste is one. Cool. There's another kind of non-Newtonian fluid, and it's one where the viscosity appears to increase as the shear rate increases. So it starts off thin, right? And then as you shear it faster and faster, it gets thicker, thicker, and thicker. This is shear thickening. I'm going to let you guys try to think of a shear thickening fluid. All right. Hopefully you've seen a YouTube video of this, but cornstarch in solution is a shear thickening fluid. Silly putty is. So when you pull silly putty very fast, it tends to just break as opposed to flow. And that's because it's a shear thickening fluid. Cornstarch in solution is a shear thickening fluid. And the reason both of these are shear thickening fluids is they have these long chains that get interwoven. And when you shear them at slow amounts, the chains can untangle themselves. But as you shear them faster and faster and faster, the long chains of molecules get entangled in each other and greatly increase the resistance to that shear. I would highly recommend you spend, I don't know, less than 3 hours and more than 10 minutes watching cornstarch videos online. It's fantastic. The joy people feel, I want to do this someday, I've yet to do it, when they walk across liquid cornstarch is amazing. But if you look closely, when they put their hand into the liquid cornstarch, or as they run across, you'll see the cornstarch solution stick to their feet in a weird way, right? And the reason it sticks to their feet is as their feet, let's see if I can draw a foot here. That's a weird heel. That's a heel, trust me. Heel. As their heel pushes down on the fluid has to come around the heel, and we have a very fast, very high gradient in the liquid here near the heel, right? And low gradients away. And we know that if we have a high gradient in the velocity, if we have a high shear rate, that these molecules get all tangled up and it turns to look like a solid. It's really weird. So as they take their feet out, you'll notice that their feet are all lumpy because there's all this cornstarch solution stuck to their feet where the shear stress is the highest. There are also fluids which become shear thinning. As you shear them, their apparent resistance to the motion decreases. All right, so again, pause the video, think about this, try to come up with some answers about things that you know that seem to get more slippery as the faster you shear them. All right, so one you might not have thought of is shampoo. And the reason shampoo is, I think there may be two O's there. Shampoo is shear thinning is you want it to be able to easily, you want it to stay together, right? So when you squeeze it out of the bottle onto your hand, you don't want it to run immediately off of your hand onto the ground. But when you start to lather it in your hands, you want it to actually become thin so that it can easily mix with the water. Latex paint is a similar one, right? We want latex paint to easily coat a wall. So when you shear it with a paintbrush, if this is our wall, and we have a paintbrush, let's see if I can draw a paintbrush here. That's not the worst paintbrush. So as the paintbrush is going down, we have a high velocity here and V high here and zero velocity here. And in between, this shear stress is quite high. And so the apparent viscosity of the latex paint becomes small, and it coats very evenly. Then, as you take away this paintbrush, the paint is no longer experiencing a lot of shear, and its apparent viscosity increases, which prevents it from running down the wall and beating up, right? Because one of the things, and we'll talk about surface tension in a couple lectures maybe, but surface tension causes liquids when they're on a flat surface to beat up, and you want that to be prevented, so you have a very thick fluid when it's not under high shear rate to prevent that from happening. And then if it doesn't beat up, it doesn't run down the wall, and everything works out happy. So shampoo, latex paint. And the reason that these become shear thinning is because they are also composed of long molecules, but as you shear them, these molecules align and flow past each other very neatly. And then as you stop, they tangle up just a little bit. Not quite as much as the silly putty and cornstarch, but they definitely tangle. So at low shear rates, this tangling is important, and at high shear rates, they actually untangle and align and flow smoothly past each other. You'll notice some aggregates, like slurries, will also become shear thinning for this very reason. They're full of little particles that align and organize, and then when you allow them to come to a rest, Brownian motion causes them to retangle and become randomized again. All right, let's do an example problem about shear stress. We want to know what the moment is to return this top plate at a rotational velocity omega. So we have two flat circular plates, one stationary, one moving at a rotational speed omega. This has a radius of capital R, and it's filled with a fluid with viscosity of mu, and they're separated by a height h. So we got to first choose a model that we're going to use to try to predict how this system is going to behave, right? So the model we want to choose is going to relate motion to shear stress, which kind of tells us that we're going to want to use our model for that tau is equal to mu du dy, which is also for very particular situations, kind of like this where you have flat plates moving past each other, is equal to mu times v over h. Remember, this is only true when our gradient is constant. Great. And the other thing we're going to want to use is that our moment is equal to r cross f. Okay? So now we're going to work towards a solution combining models if necessary. Let's label these as equations 1 and 2, and we're going to have to make some explicit assumptions. We're going to assume Newtonian fluid. And there's two reasons we're making our assumptions explicit. One is for our graders. May they ever be in our favor? Anyway. Graders, because we want them to understand what they do. And I think I explained this in another video, but when I instruct our graders to grade, what I instruct them to do is give points that for demonstrated understanding of a problem. There are some exams you see where it looks like somebody loaded a shotgun full of all of the equations and keywords they know, and then they shot it at their page, and they're just hoping for as much partial credit as they can get. And they don't get much partial credit under my grading schemes, because you have to demonstrate understanding. And the way you can demonstrate understanding is showing how your assumptions are related to your equations and your equations are related. Another thing we're going to assume is that our radius is much, much larger than our height. So we're going to minimize our edge effects. And C, we're going to assume that omega is small. So we're not spinning this thing super fast. All right, so we're going to start with equation 2 and turn it into equation 2 and turn it into equation 3. And we're going to say that our moment is equal to tau cross r. Sorry, I got that backwards. R cross tau times our area. Now, our shear stress is changing across our plate because our velocity is changing across our plate. The rotational velocity is constant, but the actual velocity is not. And so we're going to do ring integration. I think that's what it's called. Here's 1. There's 2. So this is dr, some differential radius area, and it's at some radius r. And so we can say 3 to 4 that our moment is equal to tau, some differential moment, is equal to, wow, I really want to put tau first, don't I? is equal to r cross tau times our differential area, which is going to be 2 pi r dr. So 4 to 5, our differential moment is going to be equal to let's take out this cross product here. I'm tired of this vector notation. So this is going to be equal to tau times r times 2 pi r dr times the sine of 90 degrees, because our velocity is in this direction, but our radius is in this direction. So they're always 90 degrees to each other, which is great because that's just equal to 1. Wonderful. And we can also simplify our tau. So 5 plus, this is where the numbering becomes useful, 5 plus 1 gives us 6. We say that our differential moment is equal to mu times v over h times 2 pi r squared dr. But our v, right, is really just equal to 6 into 7. dm is equal to mu times omega times r over h times 2 pi r squared dr. Oh, wonderful. Our velocity is really just equal to our rotational velocity times our radius divided by it. And then our velocity gradient, our shear rate, is just that velocity divided by the h, the separation of our plates. So now if we want to get our total moment, m is equal to the integral of dm, which is equal to the integral of mu omega over h 2 omega over h times pi r cubed dr, integrated from 0 to our whole radius, which is equal to mu times 6, almost got that wrong, mu times pi over 2h times omega r to the fourth, evaluated from 0 to capital R, which is equal to mu pi omega capital R to the fourth over 2h. Oops, not capital H, just h. So like I said, this can actually be used to measure the viscosity of a fluid. If you know h, the separation of your plates, and you know the rotational speed of your plate, and you know the radius, and the only thing you don't know is and you can measure your moment, then you can calculate your viscosity, and these are called rheometers. They're quite expensive, but they are also quite useful. Yeah, great. So next video we'll start talking about fluid statics.